Welcome to next session on Module 4. In this session, we'll discuss about optimal scheduling of hydrothermal plants. So here, we go for a hybrid combination of thermal power plant and hydel power plant. A represents thermal power plant and B represents hydel power plant, because most of the times throughout the country, we cannot just depend on one type of source. We always go for hybrid combination to meet the load requirements. So A is thermal power plant, B represents hydel power plant, and PT represents power generated by thermal power plant, PH represents power generated by hydel power plant, and together they are meeting a demand PD, which represents total load demand. So we are considering this hydrothermal power plant combination or a hybrid combination. And next, from this diagram, we can see that thermal plant is providing power PT, hydel power plant is providing power PH, PD is the demand it is serving. And here, when it comes to hydel power plant, we have the water inflow represented by J and water discharge represented by Q. Water discharge is nothing but the water that is discharged from the generating plant after being used for power generation. So the generation of thermal plant, if it is PT and hydel plant be PH, total load supplied will be PD and the losses happening in the system will be PL. Now, the aim of optimal load scheduling will always be to minimize the total generating cost of not only thermal plant but also hydel plant for that matter. Because when it comes to thermal power plant, fuel used is coal, so cost comes into picture. But when it comes to hydel power plant, water is available free of cost for power generation, but yet we have to consider its optimal operation, that is optimal usage of available water itself can be considered as optimal operation or economic operation. So here, uh, the operating cost generally will be significant only in thermal power plants because coal is involved. But we have to think about the constraints of water availability for power generation in hydel plants. So, in order to discuss this, we go for mathematical modeling, which is called as mathematical formulation. So, for conducting any analysis under generation, we have to consider a specific duration, capital T, either 1 day or 1 year or 1 month of continuous operation. So, during this period, fuel cost must be as minimum as possible, and water availability under specific condition, that is as much as possible without much wastage, the water must be utilized for power generation, and the transmission losses also must be kept in consideration. So we'll go with some assumptions. The various assumptions are: storage of hydro reservoir at beginning and end of the period T are specified. The hydro reservoir before going for power generation, what was the level of water available in the reservoir? And after the power generation is over, what is the availability of water at the end of specified duration must be known. From this we can get to know how much water was being utilized. Then second one, water inflow into the reservoir and load demand on the system must be known. How much water is flowing into the reservoir from available natural facilities, and load demand on the system also must be known. Next, let x of capital T be the level of water in the reservoir at the end of period T. X naught be the level of water in the reservoir at the beginning of period T. So X of T is water that is available after the water has been used for the power generation. X naught is the initial level of water uh, before the power generation process. J of T represents rate of inflow of water. At what rate with respect to time? How many gallons or how many liters of water is flowing into the reservoir with respect to time is defined by J of T. If you integrate that with respect to time, we get total inflow of water. Q of T represents rate of discharge of water. Now 0 to T, Q of T dt will give us total discharge of water. When it is integrated with respect to time, we get the total discharge of water. Then we define water availability equation. X of t minus x of naught plus 0 to t q of t dt is equal to 0 to t j of t dt. Means total inflow of water is equal to total water that is being spent. So total water spent is nothing but water spent for generation plus water being discharged. If we add water spent for generation and water being discharged, we get total water that is being spent in the reservoir, spent from the reservoir, and then total water that has been into the reservoir is on the RHS. So those two should be equal. This is water availability equation. So the LHS part defines the draining of the reservoir or emptying of the reservoir. Right hand side part defines the filling of the reservoir. So both of them should be equal at any point of time. If you write it in the form of an equation, xt minus x naught plus 0 to t qt dt minus 0 to t jt dt is equal to 0. Then the power balance equation which is applicable here is pt plus ph minus pd minus pl is equal to 0. PT is power generated by thermal power plant, PH is power generated by hydel power plant, minus demand minus losses should be equal to 0. We very well know the standard power balance equation is total power generated should be equal to total power demand plus losses. Now total power generated here is split into PT and PH from two different sources, and PD and PL are demand and losses. So the solution for this mathematical model will define the solution for this problem, that is hydrothermal combination problem for optimal operation. So when we take thermal power plant, the optimal operation is to see to that it should satisfy the exact coordination equation which we have defined earlier in module 3. We have talked about exact coordination equation that has to be satisfied. And when it comes to hydel power plant, the efficient usage of water comes into picture, so it should satisfy equation 1 and 2. So equation 1 minimize the problem is to determine variable q of t. Here we have to find that q of t, which is discharge of water in equation 1, to minimize the cost of generation. So q of t will be generally assumed initially, then as per the iterative procedure, q of t will be updated later on. Lambda also has to be found for thermal power plant, which is incremental fuel cost. So value of lambda as usual and q of t will be updated in successive iterations. So value of q of t, which satisfies both equations 1 and 2, at the same time minimizes lambda in case of thermal power plant. Altogether this will give optimal solution. So using this, optimal thermal power plant algorithm can be understood. So this finishes optimal scheduling or optimal load dispatch of hydrothermal plant. We'll continue with the next topic in the next session video.